Hi everyone, welcome to our first lecture on transformers. This is a first lecture in a series of lectures in which we'll discuss this topic. Hopefully, over the course of next few lectures, we will talk about how to model transformers, how to analyze them, and what transformer tests we have in order to determine the parameters of this element. So what is a transformer? A transformer is a device that changes the AC voltage from one level to another. You have an input voltage, and this device allows you to change the magnitude of the output voltage. If the output voltage is higher than the input voltage, we call this a step-up transformer. This is a transformer that raises the voltage. If the output voltage is lower than the input voltage, we call it a step-down transformer. And of course, there are cases in which the input voltage and output voltage are of the same magnitude. We call these one-to-one transformers or isolation transformers. We're not going to be talking about these type of transformers in this lecture, but we'll focus on transformers that either step up the voltage or step it down. A very interesting thing about transformers is the fact that it does change the voltage level without affecting the power. So you can raise the voltage or lower it without changing the input power that is applied to the device. We will see this more in terms of the mathematical equations of why this happens exactly, and we will see shortly why this is so important in the operation of the power systems. Now, the basis of transformer action is Faraday's law. This law states that if I have a magnetic flux phi and I apply it to a one-turn coil, it will induce a voltage in the coil, and the magnitude of this voltage is going to be proportional to the rate of change of the magnetic flux. Mathematically speaking, E, the induced voltage, as you can see it on the slide, is going to be equal to the negative of derivative of flux with respect to time, which is essentially the rate of change of magnetic flux. This, of course, is an equation for a one-turn coil. If I have a coil with more than one turn, which, as you can see in this diagram, I have a coil with n number of turns, the equation changes to E equals minus n times derivative of flux with respect to time. So the essence of the equation is going to be the same, but the voltage induced is going to be related and proportional to the number of turns that you have in the coil. In this equation, you notice something interesting. There is a negative sign here, so E is in fact minus derivative of flux with respect to t. This minus sign is not included in our calculations. We just place it there to indicate the polarity of the voltage, and this is called the Lenz's law. Lenz's law indicates that if you apply a flux to a coil, the voltage induced in it is going to have a polarity in such a way that if you short circuit that coil, the current flowing in it will produce another magnetic flux which will oppose the original flux. Let's see what that means in this diagram. This is my coil, which, as you can see, has n number of turns, and I have applied this magnetic flux phi to it. Now, the direction is going to be in such a way that the polarity of voltage is going to be in such a way that if I short circuit this coil, the current flowing through it has to generate another flux which will oppose the original flux. If I want to oppose this original flux, the opposing flux has to be a direction from top of the page to the bottom of the page. And using Ampere's law, in order for me to generate this flux, I have to have a current flowing through this coil in the direction that I have shown, which is the same as this direction here. So the current is going to flow like this, and like this. For this current direction, the polarity of the voltage is going to be positive and negative terminal. So this is what the Lenz's law does. It essentially indicates what the polarity of the voltage is going to be. But remember, we don't include that in our calculations. So in your circuit calculations, your voltage is going to be simply derivative of flux with respect to time. Okay, now we're ready to analyze an ideal transformer. A transformer in general consists of two very important elements. One is the magnetic core, and the other one, two windings. These two windings, we refer to them as primary and secondary. They may come with different names as well. For example, some people call them input winding and output winding. But In this lecture and the remainder of lectures in this series, I will refer to them as primary and secondary. You can see that I have my primary winding on the left hand side, and I use index 1 to indicate that, and on the right hand side I have my secondary winding indicated with index 2. So primary winding has N1 number of turns here, and secondary has N2 number of turns here. If I don't connect these windings to any voltage source, nothing will happen. But imagine I have a voltage source here, and I connect my primary winding to this source. As a result of it, a current is going to start flowing in the coil, which I'm showing it here as I1. When this current flows through the coil, due to Ampere's law, I'm going to have a magnetic flux generated. This magnetic flux obviously starts flowing through the magnetic core, and in doing so, it will cross my secondary winding. Now recall what Faraday's law says. If you have a magnetic flux that crosses a winding, crosses a coil, it will induce a voltage in it. So here, I have a magnetic flux phi, which is crossing my secondary winding. Therefore, it will induce a voltage in that winding, which I'm referring to here as V2. If I don't have anything connected to this winding, in other words, if it's open circuit, nothing will happen. But imagine I have a load, which I'm showing here with an impedance, and I connect this impedance to the secondary winding. As a result of it, a current, which I'm showing here as I2, will start flowing in that circuit. So what did we do here? We have an element that by applying voltage to one winding, it induces and generates a voltage in another winding. This is step one for understanding what a transformer does. But an equally important step is to understand how these voltages are related to one another. Now, according to Faraday's law, the flux that is generated as a result of that voltage source V1, these two are going to be related to one another. And the relationship is flux is going to be negative 1 over N1, number of turns for my primary winding, integral of V1 dt. If I take a derivative of both sides, what I will get is V1 is going to be negative N, or N1 rather, derivative of flux with respect to time. This is the same equation as we saw on the previous slide. Remember this, so this is going to be the voltage for the primary winding. Now, what about the voltage that is induced on the secondary winding? According to Faraday's law, this voltage is going to be negative of N2, number of turns for the secondary winding, derivative of the flux that crosses it, and notice this is the same flux that crosses the primary winding. So now I have one equation for V1 and I have one equation for V2. If I divide these equations by one another, the two terms derivative of flux, which are the same, would cancel out, and I will have this equation that I'm showing here. The ratio between V1 and V2 is the same as N1 and N2. So V1 over V2 equals N1 over N2. I call this A, and this is my turns ratio for the transformer. Now, a few things here. Notice that on top of all my variables, my V's and I's, I have a tilde sign. This is my notation, this is my convention to indicate that these are phasors. These are complex values. These are not scalar values, so in fact they have a magnitude and a phase angle associated with them, number one. Number two, remember we talked about a step-up transformer and a step-down transformer? I said a step-up transformer is a transformer that increases the output voltage with respect to input. Now, if I call my primary winding here my input and my secondary winding my output, if I want a higher voltage on the secondary side compared to primary, that means I want V2 to be greater than V1. The only way this happens is if I have N2 greater than N1. That means I would have to have more number of turns on the secondary compared to primary. Following the same logic, if I have a step-down transformer, That means I would need to have less number of turns on the secondary compared to the primary. So the number of turns directly indicates whether I would have higher voltages or lower voltages. Now that we know how a transformer affects the voltage, let's see how it impacts the current. We're going to consider the same example as before, one transformer, two windings. Let's assume, similar to before, that I connect my primary to a voltage source, and my secondary I connect it to a load impedance. As a result, I'm going to have a primary current I1 and a secondary current rather I2. Now, from magnetic circuits, you probably remember that every time you have a winding wrapped around a magnetic core which has a current flowing through it, we model this as a magnetomotive force. Magnetomotive force essentially is the effective current that is being applied to that core. The current that generates that magnetic flux, and the magnetic flux starts flowing through the magnetic circuit. So for the first winding, I can model it in an equivalent circuit in the form of a magnetomotive force. This magnetomotive force, again, I'm not going to get into details of this. I'm assuming you remember this from your magnetic circuit courses. I model this as an equivalent voltage source, and the value of it is going to be N1 times I1, the number of turns times the current that is flowing through it. I can do the same thing to the secondary winding, and this is going to be N2 and I2, or N2 times I2. There are no other coils, so essentially these two are going to be connected to one another. And in this equivalent circuit, I have two voltage sources that are connected in parallel. They have to be equal. If they are equal, that means N1I1 equals N2I2, as you can see in this equation. And if you work with this equation a little bit, I1 divided by I2 equals N2 divided by N1, or 1 divided by turns ratio A. You immediately notice a difference between the impact of the transformer on voltage and current. Let me write this here for comparison purposes. So V1 tilde divided by V2 tilde is N1 divided by N2. What does that mean? That means if I have more number of turns on the secondary side compared to the primary, this transformer will step up the voltage. So the secondary voltage is going to be higher than the primary voltage. On the other hand, if I have an N2 which is greater than N1, you can see that your I2 will be lower than I1. So a transformer that steps up the voltage steps down the current. A transformer that raises the voltage lowers the current. A transformer that lowers the voltage raises the current. So what a transformer does to voltage is opposite of what it does to the current. This is the most important thing that you should remember about transformers. They do opposite things to voltage and current. Lower one, raise the other one. Before we move on, let's review a few important things about transformers. You notice that I keep mentioning ideal transformers, and you may wonder what is the difference between an ideal transformer and a real transformer. The answer is lack of losses. Real transformers have losses, have resistive losses, they have core losses, they have flux leakage. In an ideal transformer, we assume that none of those exist. Everything is ideal, we have no losses. In other words, the efficiency is going to be 100%. In the future lectures, we will see how to deal with these non-idealities and how we actually model them. But for now, we ignore all those non-idealities and all those losses. Number two, remember that what a transformer does to voltage is opposite of what it does to current. If it increases the voltage, it reduces the current. If it reduces the voltage, it increases the current. In defining that, I use the notion of turns ratio A. Be very careful when you use that notion. Why? Because different people define it differently. I define A, turns ratio, as the ratio of the number of turns on the primary side divided by the secondary side. So A, by my definition, is N1 divided by N2. Some people might define it as N2 over N1. And as a matter of fact, a lot of people do, and instead of A, they use the letter K for it. Regardless of what letter people use, pay attention to how it's been defined. Is it the ratio of primary to secondary or the other way around? Final important point is the dot convention. In all the transformers, you notice there are two dots, two black dots associated with the windings. These dots are placed there to help you understand what the polarity of the voltage is and what the direction of the current is. So this is the dot convention. I have redrawn that circuit from the previous slide, minus of course the magnetic core. You notice I have two windings. One of them has N1 number of turns, one of them has N2 number of turns. Turns ratio is A to 1. In other words, A equals N1 divided by N2. I have a voltage on the primary side V1, I have a voltage on the secondary side V2, and I have the two currents I1 and I2. Dot convention says when it comes to voltages, any terminal connected to a dotted terminal is positive. So this terminal that is connected to the dotted terminal has a positive voltage. This terminal that is connected to this dotted terminal has a positive voltage as well. Dot convention for currents is a little bit more tricky. It says when one current enters a dotted terminal, the other current has to leave the dotted terminal. So notice in this diagram, I1 enters the dotted terminal. As a result of it, the direction of I2 is in such a way that it leaves the dotted terminal. So these are the important things that I want you to remember about transformers. The notion of turns ratio, what the transformer does to voltage and current, and the dot convention. You probably remember in the beginning of this lecture, I mentioned a transformer changes the voltage level from one level to another without affecting the power. And you may ask yourself why? Well, part of it is because we're assuming that this transformer is ideal, so there are no power losses anyway. Let's see this, however, in terms of mathematical equations. If I have a voltage on the primary side V1 and a current on the primary side I1, and there is a phase angle difference between them, let's call that theta 1, you remember that power on the primary side is V1 I1 cosine of theta 1. Following the same logic, power on the secondary side is going to be V2 I2 cosine of theta 2. A transformer only changes the magnitude of voltage or magnitude of current, not the phase angle. So if I have a phase angle difference on the primary side, theta 1, this is going to be the same as the phase angle difference on the secondary side, theta 2. So for now, let's just assume that these are equal. I'm going to rewrite the power equation that I have for the secondary, and you will notice something interesting. P2 is V2I2 times cosine of theta 2. Now, instead of V2, I replace it with V1 divided by A. That basically comes from the main equation, voltage equation for the transformer. The main current equation for a transformer indicates that I2 is going to be A times I1. Remember this, V1 divided by V2 was A, and I1 divided by I2 was 1 over A. This is how I got these two equations. So now I have a 1 over A and I have an A, so I can cancel these out, and this equation becomes V1 I1 cosine of theta 1, which is the same as P1. What does it tell me? P2 equals P1. What does that mean exactly? That means an ideal transformer does not lose power, does not generate power. Power goes from primary side to the secondary side. Do remember, however, this is for an ideal transformer. A real transformer will have power losses. We'll talk about that later. Next, we can apply the same thing to reactive power. Reactive power is going to be V2I2 sine of theta 2. If I follow the same logic, my Q2, reactive power on the secondary side, will be equal to Q1, reactive power on the primary side. And of course, I can extend this analysis to the complex power. So the complex power on the secondary side is going to be the same as complex power in the primary side. Now that we understand what transformers are, this is a good place to talk about why they are necessary. In order to do that, picture a power system. Imagine there are no transformers, so you have a generator, a power plant, and a load area, let's say a particular city. If you want this power plant to provide the power for the load area, you have to connect them. This connection can be through overhead lines or underground cable, for example. Regardless of what you use, these lines are going to have resistances. And as a result, when the power goes from the generation side to the load side, the current flowing through this line is going to lead to ohmic losses, resistive losses, voltage drop. Typically, load areas are far away from generator areas, so that means you're going to have a significant voltage drop to an extent that the system is not going to be able to operate. In order to solve that problem, we use transformers. Remember, a transformer does opposite things to voltage and current. So if I use a transformer to step up the voltage, what's going to happen to the current? It's going to come down. If I have lower current, that means a smaller amount of current flows through the line. That means I'm going to have less losses. So less voltage drop and less resistive losses, which is exactly what we want in power systems. Take a look at this diagram on this particular slide. This is a schematic diagram of a typical power system, especially in North America side. So here you would have your generators, and let's say this is your load area. Instead of connecting them directly to one another, you make the connection through transformers. First step is to use unit transformers to step up the voltage. Remember, when you step up the voltage, you lower the current. So you're going to have less current flowing through the line for the same amount of power. So first thing we do is we step up the voltage to the transmission level voltage, which is 230 kV to 750 kV. We do have higher voltages as well, but these are the more common ones. This power comes from the generation side closer to load area. Now that you're getting close to load area, you obviously have to start reducing the voltage because you're not going to be able to bring a 230 kV voltage to a household. However, reducing the voltage happens in different stages, not all at once. So the first thing you do, you use a transformer to step down the voltage from transmission level to sub-transmission. So essentially, from 230 to 750, you come down to 69 kV to 169 kV. You bring that power closer to the load area. As you get even closer, you use another transformer, which is going to be your substation transformer for the distribution level. Here, you lower the voltage from sub-transmission level to something in the range of 600 volts to 35 kV, 35,000 volts. And then you bring this power even closer to the load area to the individual customers, and finally you're going to have one final transformer which comes with different names. Some call it distribution transformer, load transformer, service transformer. All of them mean the same thing. This is a transformer that is connected to the distribution system, and it's directly supplying and feeding the customer. Here, from a 600 volt to 35 kV voltage level, you bring it down to 120 volts or 240 volts, which is the voltage suitable for household appliances. Notice I raise the voltage on the generator side and then start lowering it until I get to the load area. The key thing is generation areas are very, very far away from cities. So as a result of it, I increase the voltage so that current goes down and I don't have significant voltage drop and ohmic losses. This part of the network is called transmission. This part is called sub-transmission, and this part is called distribution. This is how a power system operates. Transmission, sub-transmission, and distribution networks connect generation areas to load areas. Another interesting feature of transformers is what they do to impedances. The value of the impedance would be different depending on where you're looking at it from, whether you're looking at it from the primary side or the secondary side. We call that impedance transformation. In order to understand this, let's consider this example. I have a transformer with a primary winding and a secondary winding, and I have connected a load impedance to the secondary side. if I look at this load impedance from the secondary side, in other words, I don't know what exactly is connected and I want to measure how big it is, all I need to do is to have a voltmeter and an ammeter to measure V2 and measure I2, and V2 divided by I2 is going to be my impedance. It's very simple. However, imagine someone wants to measure the value of the impedance not from the secondary side but from the primary side. In other words, imagine this someone does not know how the transformer looks like, what the load is. From that person's perspective, the transformer and the load is like a black box. All this person has is a voltmeter and an ammeter on the primary side. So in order to measure the value of the impedance that is connected to the transformer, this person would divide the voltage by the current. So you would divide V1 by I1. V1 obviously is A times V2. I1 is I2 divided by A. You simplify this equation, you will get A squared V2 over I2. However, what is V2 over I2? It's basically your Z load. So the value of the load impedance that you see from the primary side is the actual load impedance times A squared. This is a very important aspect about transformers, and we'll come back to this when we want to define the equivalent circuit of a transformer. When you take a quantity, you look at it from the secondary side, it has one value. When you look at it from the primary side, it has a different value. And the ratio between the two values is basically going to be the turns ratio squared. We call this referring quantities from the secondary side to the primary side. Of course, you can do the other way around. You can refer quantities from primary side to the secondary side as well. Now, referring quantities, why does it matter? Let's do this through an activity. Imagine you have a speaker with an impedance of 10 ohms, which is going to be this load for you. And this is fed by a 110 volt power supply through a transformer with a turns ratio of A, and we don't know what A is. The cable connecting the power supply to the transformer, which is this element here, has an impedance of 2 ohms. So I have 10 ohms here and 2 ohms here. What I'd like to do is to find the appropriate turns ratio for this transformer that maximizes the power transferred to the speaker. At this point, I'd like to ask you to pause the video, work through this activity a little bit, and when you're ready, hit play so that you can see the answer. Okay. From circuit theory, you probably remember that if you have a voltage source and two impedances, Z1 and Z2, maximum power will be transferred to Z2 if Z1 equals Z2. What are the Z1 and Z2 in this case? I have a Z cable, which is 2 ohms, and a Z load, which is 10 ohms. Obviously, they're not equal, so maximum power will not be transferred to your speakers. However, notice that this is 10 ohms on the secondary side. What you need to do is to see how big of a impedance you have on the primary side. In other words, if this is your source, this is your cable, which is 2, you want to know from the primary side or from here what impedance you're measuring. Going back to what we talked about on the previous slide, this is going to be A squared times 10. In order to have maximum power delivered to your speaker, the two impedances have to be equal. In other words, A2 times 10 has to be equal to 2, which is A equals to 1 over square root of 5. This is something that you can do only with transformers, and we call that impedance matching. By choosing the right turns ratio, you can determine a situation in which maximum power will be transferred to your load. This brings us to the end of our first lecture on transformers, on ideal transformers. This is a very good reference that I used for parts of this lecture, the book by Chapman, and if you're interested, I encourage you to read Chapter 2, which is specifically on transformers.